Thank you, Monty. So first of all, I would like to apologize for the last minute changes we had last week for my fault that it was independent of my will, but I disrupted a little bit the program. And for this, I want to thanks a lot to the IPAM staff for the support, and Benjamin Sable for replacing me just immediately, almost immediately. And also I would like to thank Benedetto Piccoli that it was supposed to speak right now and kindly let me his slot because I'm in Europe and it's 5 o'clock in the afternoon, and I was afraid to be too tired in 1.5 hours to deliver the lecture. So many thanks to you all. So I rearranged a bit my slides because I know that last week my colleague talked a lot about traffic flow models, in particular about macroscopic traffic flow models. So I hope not to repeat too many things. What I plan today is to just give a brief introduction to macroscopic model, to at least set the notation, and that probably changes with every speaker, and to introduce the main tools that are needed to the following. And then I would like to concentrate in particular on macroscopic models taking into account autonomous vehicles. So how we can describe the presence and the impact of autonomous vehicles in the traffic flow. So, as you have may listened a lot of time this last week, we have mainly two approaches to describe traffic flow. One is the microscopic approach, in which you basically try to follow each car trajectory, and you come up with a larger system of ordinary differential equations involving a lot of parameters. So a number of parameters for each equations, and therefore the computational cost for running such models is proportional to the number of agents. And it's also they are also harder to calibrate in the sense that there are many parameters to be calibrated. So this type of model are mainly used to describe and understand small setting, like, for example, the one that I put in the picture, so a junction, a road junction, or I mean, some small part of the road network. On the other side, we can see traffic from a very far point of view, so like a continuous flow, not caring much about each single car, but mainly of macroscopic quantities like that I will introduce in the next slide, like the density and the flow. That will be described by one or two partial differential equations involving a low number of parameters. And in this way, we can cover a much larger portion of networks in a reasonable with a reasonable computational effort. And moreover, we can rely on a well-developed mathematical theory, analytical theories for this equation, and set properly control and optimization problems. So I will focus, as you understood, on the macroscopic models, trying to add the autonomous vehicle component in this. So, as I was anticipating, what we are interested in are not the single car trajectories here, but some averaged quantities, some aggregate quantities, like the traffic density, that can be seen as the number of vehicles per unit space. So how many vehicles are in, for example, 1 mile or 1 kilometer for house in Europe. And the mean velocity, so the distance covered by vehicles in unit time, again, these are averaged quantities. So we are not looking at each single vehicle, but we just take the mean of the different velocities, and the traffic flow, that is the number of vehicles that pass at a given point per unit time. Of course, we will see how this quantity behave mathematically, but of course, if we want to apply the models, we also have to be able to measure this quantity to calibrate the model on the specific situation we are looking at. And for this, we have a number of data sources that allows us to measure some of these quantities, some directly and some are derived by, can be derived by the others. So nowadays, so the most classical measurement tool are the magnetic loop detectors that are that can count the vehicle as they pass by at a given point of the road. But nowadays you can also use video recordings, data coming from the GPS installed on the cars and other devices. So you have a lot of information in principle to take to calibrate the model and describe what is happening on the road. So just to give you an idea of how this data look like, because when I started working with this, I had no idea of how the data were looking and how to deal this with data. So here I show you an extraction of a file containing loop detector data. So this is the raw file that you seldom have access to. So in many data sets, the data are already pre-treated, so you often have access to the quantity of interest, like the flow, the density, and the mean speed. But the raw data, what they look like, are like this. So here, for example, you have a file that corresponds to data coming from a collection of loop detector on the road network around Marseille in the south of France, so not far from here. Here I'm close to Nice. And in this file, there are all the data that have been recorded in the first minute of the 1st of September of 2015. And all the loop detectors are mixed. So in the first column, you have the loop code, so the loop identification code. Here is some information about the exact position on the road. And here is the day, so it's a Tuesday. The data are in French, so I'm translating for you. Here is the date, it's September 1st. Here is the hour, so it's the first minute after midnight. Here are the second and the hundredth of second. Here is the lane, so C is for the central lane, this is for the right lane, it's the droite in French. And here is the speed of the vehicle that was passing exactly at this moment in the central lane. And here is something that should be the length of the vehicle in decimeters. So, okay, this should be a vehicle of 1 meter long. So I guess there are errors in this in this data. So, but more or less, these are the information you can recover from loop detector data. Loop detector data are interesting because they count all the vehicle passing through at that point, and so you know how many cars are on the road. So you may have an idea not only on the flow at that point of the road, but also on the amount of vehicles, so the density somehow. Yet these detectors are, are fixed and are not present everywhere. So you don't have access to this type of measurement everywhere. So that's why in the recent years, traffic engineers have been using other sources of data, like, for example, data coming from GPS. The GPS that are on the cars. So here now the problem is that not every car has a GPS on it, at least in Europe. And so you don't know exactly how many cars are on the road in that moment. So, and the penetration rate may vary a lot from one place to another, from one time of the day to another time of the day. So you hardly have the information on the amount of cars that are on the road, but you have very precise information on the speed, that is this column here, and of course on the location. Here, these are the GPS location of the vehicle and the direction. So these are partial measurements, but that can be deployed on every point of the network as soon as there is some vehicle that is equipped with the GPS running there. And we may expect that with the deployment of autonomous vehicle, a lot of this data, there will be much more, even more data of this kind. So no matter the sources of the data, what you get, and what you already seen several times last week probably, is the fundamental diagram that you can recover from this data looks like this. So if you plot the flow against the density, so after, after that data treatment, because you saw that from the raw data don't give directly this information, but finally what you get is always something of this kind. So the plot on the left is taken from loop detectors, one loop detector, a specific loop detector here. And the data on the right are derived from car floating data, so from the GPS, after rescaling, taking into account the penetration rate of vehicle equipped with GPS. So you can distinguish, as you probably already know, a part of the fundamental diagram that shows a more or less linear dependence, but at least a one-to-one dependence of the flow against the density, and that this is what is usually called the free flow phase, and a cloud of points for which at each given density we have many different values of the flow that correspond to congestions. So when the traffic is congested, what you recover from the data are these points here that are scattered in 2 dimensions in the fundamental diagram. So coming to macroscopic models, so once we have these macroscopic quantity measured, somehow we want to construct a model that can describe the evolution in space and time of this quantity in order to make simulations, make prediction, and maybe control and optimize the traffic. So the basic idea behind the macroscopic traffic flow model is the mass conservation laws. So if you are given a stretch of road without any on-ramp and off-ramp along it, just an enter point and an exit point, you want that the car that enter in A will exit after some time in B, and that we don't lose neither create vehicles. Okay, so we want that the number of vehicles, that is the integral on the interval A and AB of the density, is conserved. That means that if we take 2 different times, T1 and a bigger time, T2, the number of vehicles present on the road at time T2, that is given by this integral here, is equal to the number of vehicles that was present in the road at the previous time, T1, plus the number of vehicles that entered the road at the upstream point, that I denoted by A, that is given by the integral of the flux on the time interval T1, T2, minus the vehicle that exited the road at the point B, so on the downstream point. And that's again the integral of the flow at the point B. So this is just the conservation of the number of vehicles, and this equality can be rewritten using the Divergence theorem as the integral of this partial differential equation that must be 0 on every interval of time and every space interval. That means that we recover the what we call the mass conservation law, that is the partial derivative of the density rho plus the partial derivative in x in space of the flux function q must be equal to 0. So this is where the macroscopic model comes from. This is just mass conservation. So we come up with this type of equation that's an equation that is well known in fluid mechanics because it's an equation that appears in gas dynamics and with other equations, of course. But yet we have to take into account that we are not dealing with a gas or a fluid now, but with a very specific system that is traffic. And traffic has some specific characteristics that make it different from a gas or a liquid, and that must be described by our model. So first of all, we want that no information propagates faster than vehicles. So the propagation speed of this equation must not run faster than the vehicle. Then we assume, as I showed before, that the fundamental relation that links the flow to the density and the speed. So the flow is just the product of the density and the speed. So here I can replace Q by rho times V. Okay. Of course, I want this quantity to stay positive and finite in time and space. I don't want to have negative density, of course, and neither negative velocities, because I'm trying to describe the traffic flow on one lane or one or more lane, but running in the same direction. So I don't want vehicle to come back, but would be problematic. And so there are all these differences with respect to fluid dynamics. So there is a preferred directions. The preferred direction, there is in principle no conservation of momentum and the energy that are the other equations that appear in fluid dynamics. We don't see, we don't speak about viscosity, and also we may question if the continuum assumption is valid here, because the length scales are not what is usually assumed in the continuous mechanics. So there are, a number of requirements and also a number of limitations of this approach, of course. So we generally do not expect to be able to describe precisely what happened on our road with such a simple model, but we may try to capture some features, and depending on the feature, to modify the model in order to get them. So as you saw, I guess Benny already talked extensively of this. The model, the basic model, the macroscopic model for traffic flow, it was introduced in the mid-50s by Lightly, Witham, and Richards. And it just consists in the mass conservation equation that we just derived before, plus a closure relation that allow to have one equation with a single unknown. Because if I write this equation here, I have two unknowns, rho and v. If now I assume that v is a function of the density only, I have just an equation for the density rho. So my problem is somehow well posed, even if it's not the correct term. So the fundamental assumption is that V is a function of rho and is commonly taken as a decreasing function of the density, meaning that when the road is empty, we can drive at the maximum allowed speed. This is what people usually do. And as far as the density increases, so there are much more and more cars on the road, we are forced to slow down, and at a certain moment when we are bumper to bumper, almost, we are stopped, and this is the point of maximal density. So mathematicians usually work with this simple speed law, that is the linear decreasing speed law, where V is the maximal speed, R is the maximal density, and using this speed equation, the flux function became a downward parabola with a maximal middle maximal point that is called the critical density, exactly at the middle between 0 and capital R. A more realistic fundamental diagram is instead preferred by engineers. That is the triangular fundamental diagram that comes out to work quite well to describe the traffic main features, and this corresponds to this type of velocity. So the velocity is constant in the free flow phase, so up to the critical density, and then decreases like this law until the maximal density. Okay, so all that I will tell you later will work with both choices, and you can also consider other choices for the speed. And what is important is that the flux function is concave down. This is the main feature. Okay, so of course the hypothesis, as we saw before, looking at the real data fundamental diagram, the hypothesis that V is a function of rho is a strongly simplifying assumption. Okay, I mean, we are asking to interpolate this cloud of points with a line. And so on one side, we agree in seeing that the LWR model is very simple, so it's easier to handle, and so it's interesting because of this, but has a lot of limitation because it is simple. On the other side, if we want to describe better some traffic features, we have to elaborate and extend the models in order to capture the feature we want to capture. And for this, okay, I won't have time to talk about all this improvement, but in the literature you can find a bunch of models that are intended to describe specific traffic feature and try to improve the scalar LWR model. So as you saw last week in Ben's presentation, there are what are called second order model, in which B is not anymore assumed as a function of rho, but it's an unknown by itself. And we have the second equation for V itself. So in this way, we can better capture the scattering of the data in the congested region. Afterwards, there have been some extensions, so some coupling of the second order model with first order model, because we agree that in free flow, first order model are enough. And while in the congestion region, we may need the second order model. And so we can couple first order and second order model in what are called phase transition model. Then there are other models explaining this scattering by stochastic and averaging tools. And then, of course, for the moment, we have thought of the road as just one nozzle, where the cars are flowing, but we are forgetting that there may be different type of vehicles, like a car and trucks, that have a different dynamics, and that's why, and this that may not be captured by the scalar model, the simple scalar model. And also there are many roads have several lanes, and this also may give more richness to what we observe in the real data. So you can find the multi-population model that I will talk about a little bit later, and also multi-lane model here. So here I didn't put the references, but I can give you some if you need. And also, and what I will show you later also, some non-local models have been developed. So, I mean, the literature is enormous. Here I just put some references, and don't hesitate to ask if later, maybe not now, if you need more references. Okay, so let's now see how we can account for the presence of autonomous vehicle in the traffic flow. And here I will present some approaches that have been developing with other colleagues. So I'm not meaning to be exhaustive, but these are some, idea of what we can be facing while trying to model autonomous vehicle on the road. So I will distinguish two cases. One case in which we are interested in a few autonomous vehicles in a traffic mainly made up of human-driven vehicles. So we will focus on the presence of one autonomous vehicle in the traffic. And then we will see how we could describe higher penetration rates of vehicles in the traffic. So a mixed traffic of human-driven and autonomous vehicles. All of these models are under development, and they are not meant to describe correctly what would happen when autonomous vehicle will be running on the road between human-driven. But they can give an idea of what could happen if the dynamics is what is described by these models. So let's focus on one single vehicle in the traffic. And the leading idea is that we want to use this vehicle to somehow impact the traffic flow. So we want to control the speed at which this vehicle moves in order to modify the traffic around it. So for this reason, the dynamic of our vehicle is different from the average vehicle in the traffic, and is described separately by an ordinary differential equation that is given here. So our model is given by the classical mass conservation law for the surrounding traffic. So we are not interested in how exactly the other vehicles, the human-driven vehicle, move. We just look them as usual as an average quantity, but we focus on the dynamics of this vehicle. So our autonomous vehicle position is denoted by y of t, so it's evolving in time, and it moves with a desired speed that is u of t, that is the speed that we want this vehicle to move. Of course, it can move at this speed if the surrounding traffic is moving faster, but as soon as the cars in front of this autonomous vehicle are slower, it has to adapt for obvious reasons. So the dynamics of this autonomous vehicle is given by so its speed is given by the minimum between the desired speed u of t and the speed, the mean speed of traffic just downstream the vehicle. So the plus sign here stands for the right trace. So it's the speed of the cars just in front of the vehicle. Of course, we are talking about averages everywhere, but this has a mathematical meaning, and we are happy. So you see that the traffic has an impact on the vehicle because the vehicle has to adapt its speed according to the traffic. But the vehicle is also acting on the traffic because it behaves like a bottleneck that is moving, because it's occupying one lane. So the cars behind it cannot, if they want to pass, they have to overtake it. And this means that basically it is reducing the capacity of the road by a factor alpha that you can see here, and I will show you better in the next slide how it is taken into account. And basically, alpha is the ratio of the number of free lanes over the total number of lanes. So it's the capacity reduction rate given by the presence of the vehicle. For example, here we have 2 lanes, so alpha will be 1/2. If we have 3 lanes and 1 autonomous vehicle, alpha will be 2/3. Okay? So we have a system made by a PDE and ODE, and they are mutually coupled because they influence each other. Okay? So mathematically, this is not easy to deal with, but this is another representation of what I just told you. So this problem of the capacity reduction. So on the road, the traffic flow is described by this flow function with maximal density capital R. At the autonomous vehicle position, the flow is reduced by a factor alpha here. And so this is the flow at the autonomous vehicle position. And this is the representation of the vehicle speed, of the autonomous vehicle speed. So it's constant equal to u. You can vary in time, but independent up to a certain density, and then it has to adapt to the traffic speed.
So, Paola, we have a question here
Yes.
from Lawrence.
I just want to look at the previous slide. I was looking at it. Sorry, I was looking at the 4th equation, the definition of the ODE, y dot. That's the V is the minimum between U of t and V of rho of t and Y of t plus. When you say Y of t plus, is it a limit from?
Yes, it's the trace, it's the limit. Yeah, because you will see the presence of the vehicle can create a jump in the density at this level. So we have to take the traces. And of course, the vehicle has to adapt to what is in front of him, to the downstream density.
But
it doesn't care of the upstream density.
Okay, but the Y of t is just the trajectory of
it's the position of the autonomous vehicles at time t.
Okay, great.
Okay.
Thank you. Thank you.
You're welcome. Thanks for the question. Yeah, please stop me if I skip something. Okay, so how do we solve here the problem? So the easiest things to do is to put oneself in the autonomous vehicle reference frame, so make a change of variable in X so that the constraint is not moving anymore, but it's fixed. And once the constraint is fixed, we know how to solve this problem because it's a conservation law with a constraint on the flux, a fixed constraint on the flux. So it is, for example, what happens at the toll gate. And we know how to describe, how to solve the problem. So basically, and okay, if you want some mathematical reference.
Sorry, I have a question.
Yeah.
So for the in your previous slide, so the PDE model you mentioned, is it one PDE for each lane, or it's one PDE?
No, no. We don't look at the lanes, but we take into account that there are different lanes in the alpha. So we allowed for overtaking somehow. Usually in the LWR model, there is no overtaking, because if you look at the macroscopic underlying model, the vehicle are not intended to overtake. So to have overtaking, either you take a multi-population model in which there is a group of cars that is quicker and a group of cars that is lower, and so they can overtake. Or, I mean, here, we allow overtaking, saying that the flow at the vehicle position is not zero, is reduced, but is not zero.
But how do you describe the position of this car?
This is the y. I have an ordinary differential equation here that gives me the evolution in time of y of t. Y is the position of the autonomous vehicle at time t. We start from a given position, and then it moves. It moves at speed u as far as the traffic is sufficiently light, and is slowed down, adapting to the traffic, and so basically mixing with the traffic when the traffic becomes too congested.
Thank you.
Does it answer to the question?
Yeah, so basically y is the longitudinal distance, right? Not the lateral position of the car.
Sorry, I didn't get your question.
So like, then do we know exactly which lane this car is in, or which alpha value this car corresponds to?
Yes, we know, we track the car, yes. The model tracks the car.
I see.
I will show you a movie and some pictures so that you can see. Okay?
Thank you.
So, okay, how to solve this problem is not easy to explain. Also because, okay, probably many of you don't know much of the theory of conservation law, but basically what we do is to reduce the problem to a problem with where the constraint is fixed. So we do a change of variable in space here, and we treat the problem as a problem with a fixed constraint. Just for a traffic example is as what happens as a toll gate. So you have a flow restriction at a certain point of the road, and this flow restriction is not moving. Okay, so basically what you want to do is to construct a solution to this problem, and to take into account the presence of this flow constraint that says that the flow at the vehicle position cannot be higher than this line here, this f of alpha of u. You have to distinguish two cases, basically, to construct a solution. So if the classical solution of the conservation law satisfies the flow constraint, you are happy. So the traffic is flowing normally, and the autonomous vehicle has no impact on it. So they are like running independently. No one bothers the other. Otherwise, if indeed the autonomous vehicle has an impact, because the classical solution, the solution that would be true if the vehicle was not there, has a higher flow than what is allowed, then you have to modify your solution. And how to modify your solution is introducing these two states that basically are these 2 points here, the intersection of the tangent with the slope u to the smaller flow with the bigger flow here. So you take these 2 points here, rho u hat and rho u check here, and you glue the two solutions. And of course, at the point x equal to u of t, u times t, that is the vehicle position, you have a jump. You jump from a density rho hat of u upstream, so just behind the vehicle, to a much smaller density that is rho u check, that is this one. You jump from here to here, just downstream the vehicle, okay? And this is something that is normally not happening in traffic, because in traffic, normally you don't have downward jumps. You can have upward jumps when you enter a congestion. So when you enter a congestion, you come from a lower density and you dive into higher density. But usually you don't have sharp changes in density in the other sense, so from higher density to lower density. But in this case, since the autonomous vehicle is there, it's somehow blocking the traffic behind and making a congestion appearing just behind it. Okay?
Quick question from Ronan.
Yes?
You're unmuted, Ronan, now.
I didn't really have a question. I think what Sharon was asking was there's some confusion with the PDE being over all the lanes, but then the AV trajectory is only on like one lane. So like, how does that interaction work?
So the model is not that precise, okay? So the model doesn't distinguish if the vehicle is on the left lane, on the central lane, on the right lane. Okay, the model just says at this position, the flow is constrained, is reduced because there is this autonomous vehicle that is running slower than the rest of the traffic. Okay, so I mean, as all the macroscopic model, it's very imprecise. Okay, I'm not taking into account all these details. Of course, you can construct a model that distinguishes each lane, that tells you where the autonomous vehicle is, exactly in which lane. But okay, it gets very complicated, and of course, I couldn't introduce this here. Okay, but of course, you can always make a model more precise at the price of complexity. Okay, and then you have to see if you are able to calibrate. Otherwise, you won't use it. So.
Okay.
So I hope to be clearer with some drawings. So okay, I should speed up. Let's imagine that we have these two density values. This is upstream the vehicle. This is downstream. The classical solution would be a rarefaction wave, okay? Because we come from higher density to lower density. But of course, if there is this constraint here, the flow at the vehicle position does not satisfy the constraint. So I have to do another path, and the new path is going from rho L to this rho hat U. Then I will jump, and this is at the vehicle position, to rho check U, and then I will come back here. In this way, at the vehicle position, I'm satisfying the constraint because I am along this line. Okay, so this is the good solution. And basically, there is this. This is the vehicle trajectory that corresponds to this non-classical shock because we have a downward jump. Okay, and it's non-classical because usually when you have a shock, mathematically the characteristic speeds should go into the shock, and here they are not. They are exiting the shock because the derivative here is smaller, so the characteristics will move this direction, and on this side, the characteristic will move that direction. But of course, okay, this is just the analysis of the model. Let's see some a movie to illustrate what is happening. So let's imagine that we have a uniform traffic flow here. So we're moving with speed at, okay, I'm sorry, I'm using kilometers per hour here, not miles, but 130 kilometers per hour. And we have our autonomous vehicle starting here, whose maximal density is set at 80, okay? And the alpha here is 0.6, so we are assuming that there are 3 lanes, more or less, okay, rounding, and 1 lane is occupied by our autonomous vehicle. And we have a constant flow coming in for a certain time, and we have some lane closure downstream that will make a queue rise on this side downstream. And so this is what happens. So you see there is this downward jump at the level of the vehicle, and at this classical shock coming backward. So if I'm running it again, okay, you have the congestion coming up because there is this lane closure downstream, and you see that the autonomous vehicle has an impact as far as the density is sufficiently small, but when the density becomes higher, it has to adapt, and basically it disappears. I mean, you see it moving, but it has no impact on the traffic. So what it means is that using the autonomous vehicle, you can modify the traffic flow somehow, and it can act as a moving speed limit. So you can use it as you usually use the speed limits to regulate the variable speed limit to regulate traffic in order to improve the flow. And here is just an example. So for example, so on the left, you see the space-time evolution of the density. So this is what you just saw before. So basically, this is the traffic jam that you saw. That is created by the lane of restriction, and so I didn't picture I didn't put the picture of the vehicle trajectory, but it should be somewhere here. Okay, so here, here the vehicle is not acting. So basically, we put its maximal density equal to 140 as the other vehicles. So basically, you don't see it because it's running as the other vehicles. As soon as you use it and you control its speed, this is what happens. So you can reduce the congestion. So you see that the congested area is much smaller, and you can then solve some optimal control problem to minimize some cost. So what we did here in this work was to minimize the flow consumption. And also to look at the average travel time and the jam length. And it came up that minimizing, so focusing on fuel consumption, we were also able to reduce the other metrics. Okay, so this is what the resulting control velocity. So you see that we make the velocity vary between basically 45 and 50 kilometers. And this was obtained used MPC control, so a model predictive control. So those who are unfamiliar, basically we are not optimizing on the whole time interval. That was, I guess, 1 hour here. So you see, we are running the simulation over 1 hour. So our scenario has 1 hour length, but we are not running the optimization over 1 hour because this is not doable in real time, so, since you don't have enough good prediction of the traffic evolution. But instead, we run the optimization on smaller interval of 15 minutes. We apply the optimal control on even smaller time interval of 5 minutes, and then we start again. So it's a real-time control process, optimal control process that we are carrying on. Okay, so here I put you some references related to this kind of approach. You can construct a more sophisticated model using the second-order models. Instead of the LWR model for the traffic, you can put the O'Rasker model, for example, as we did here in this paper, or as is done here in this other paper. Then there is the issue of the numerical simulation, because the presence of this non-classical shock at the vehicle position makes that the classical Godunov scheme or CTM model doesn't work properly, because they are not intended to capture this type of discontinuity. So you have to be very careful in order to be able to track this downward jump that appears at the vehicle position and to move it accordingly to the traffic evolution. So, so if you are interested in the numerical scheme, these are described, for example, here. Okay, this is another model that was proposed previously, in which the coupling between the PDE and the ODE is a bit different, but okay, the spirit is more or less the same. And here we have extended the approach to platoons. So instead of considering a point vehicle, so a point constraint moving in the traffic, we consider a platoon of vehicles. You can also consider a platoon of vehicles, so an interval with a certain length that can vary in time also, and that is moving in traffic and is impacting the traffic because of its presence. So instead of having a capacity reduction in only one point of the highway, you can have the capacity reduction on a small stretch of the highway, and this will have a bigger impact, of course, on the traffic flow. Okay, so there's a bunch of activity that is going on this side, and of course I'm not exhaustive here. I hope we will have time to discuss more in the following weeks. And then, okay, I think it's time to move to the other aspect. So, okay, in the previous case, I was considering just one vehicle. So now, what if on the road that we have plenty of autonomous vehicles? So either a good percentage or even all autonomous vehicles. So how they will behave, how the traffic would be. Okay, I don't know, but some years ago I designed. I start working with no local models. That are models in which the flux function, instead of depending on the density only, may depend also on an integral of the density. And so it came out that this could be applied to traffic if you imagine that when you drive, or better, when an autonomous vehicle is driving, is not reacting only to the car just in front of it, but it knows what happens even much farther and can react somehow to the evolution of the traffic around it. For this, one approach could be to consider the speed of in the LWR model, not as a function of the density at the point Tx, but as a downstream mean of the density, weighted with some weight. So in practice, if I'm here, I'm looking forward, and I'm taking, instead of just looking at this car, I'm taking an average of the density in front of me on some interval of length eta, and I'm considering this average density to adjust my speed. Of course, I find it reasonable to pay more attention to cars that are closer to me than to this one that is far away. So I may choose to take a decreasing weight here. So this omega or W eta will be a decreasing function of the space. Okay, these are some mathematical assumptions. So the other assumptions are always the same. So the speed is a decreasing function, and it's in zero, it's at some maximal values, and at the maximal density at some minimal values that can be zero. Okay, so I don't change the LWR model. I just change the dependence of the speed on the density. So this can be one choice. Another choice was proposed more recently by some colleague in Germany. And instead of averaging the density and computing the speed on the average densities, they proposed to average the speeds directly. Okay, this model has some interesting feature with respect to the previous one, and in particular that it can be more easily extended to networks. Okay, so I think that, I mean, even if I will concentrate on the previous model, this one has maybe more interest for applications. So just to tell you, okay, this model works well, at least mathematically. That means that we have all the nice features that we can expect from a model. So the density stay bounded between 0 and some maximal density. Even more, I mean, we have a strong maximum principle. So the density evolves between the minimal and maximal values it has at the initial time. And we can construct the solution to this problem. And of course, this is not obvious because now we have a flux function that is not dependent only on rho, but it's dependent on depending on t and x through this new speed law. Okay, where the density is hidden. Okay, so this is not obvious at first sight that the model has the nice features it has to have to describe traffic. So as you saw, I'm assuming that I'm looking forward, that my integration interval is from my position x to x2 plus eta, and that the weight I'm using to weight the density is non-increasing. Okay, these are obvious choices when you think you are driving, because you are not looking backward, even if, I mean, you are looking in the mirror, but and again, you have to pay more attention to what is closer to you. But what would happen to the model if we change this? So if we play a little bit with the model, we may want to change the location of the kernel support. So we can distinguish 3 cases in which we are looking downstream, we are looking a bit downstream and a bit upstream, and where we are looking completely upstream. So taking the mean of the density between x minus eta and x. So my position is X, okay? And I'm taking a constant kernel here, okay? So the monotonicity of the kernel has no impact. I'm taking a constant kernel equal to 1 over eta, and I'm fixed with that. So look at what happened. So here is, I'm starting with an initial datum with a jump discontinuity with a bigger density upstream and a lower density downstream. So this normally evolves in a rarefaction wave that is depicted here. So now what happens to my modified non-local model? If I'm taking the downstream kernel, everything looks right. But if I'm taking central or upstream kernel, you see that oscillations appear, okay? I mean, this may be true, but this is what happens to the model. Okay, and the same happens if I'm considering the opposite initial datum corresponding to a shock with the lower density upstream and higher density downstream. Again, the downstream kernel behaves nicely, so with less oscillation than the other two. And you see that in the other two, I also go beyond the maximal density. That is very bad when you drive, okay? And okay, you can run other simulation and see that again, when you take the downstream kernel, the oscillation decay more quickly than with a central kernel. And if you look upstream, things are going really bad because the oscillation increases and increases. Another criteria is the monotonicity of the kernel. So is it correct to have a decreasing kernel? Yes, it is, because if we are taking an increasing kernel, for example, like this, again, I will have oscillation appear, okay? So as far as the comparison with the classical LWR model, it seems that the choice of having a downstream decreasing kernel is a good choice. Okay, so using this model like this, so imagine that we have a street full of autonomous vehicles, and all these autonomous vehicles are using this rule. We agree that they should look forward and they should pay more attention to what is closer, but also we observe that the speed of dampening of oscillations in traffic increases with the kernel, the kernel support. So if I look very far and I take into account the dynamics of cars that are very far, with this type of rule, okay, the oscillations that are in the traffic will slow down less faster than if I'm looking just close to me. Okay, so this is an observation that must be done on this model. Okay. Then, okay, of course, one may wonder what happens if we shrink the kernel to zero, so to a Dirac delta, so the horizon eta to zero, and at least formally, it's quite clear that it converges to the classical model, to the classical LWR. Mathematically, it's less clear, so there are counterexamples, but they are very technical. For what traffic is concerned, I think that we can we can assume that we have this convergence. So here in these graphics, I changed the length of the horizon, diminishing it, and we see that we converge to the classical model profile. And on the other side, if we make eta tend to infinity, so if we look very, very, very far, we would basically behave like a linear transport equation with moving with maximal speed. And this can be seen by the numerical simulation, and that can also be proved formally. Okay, so these are just some considerations. And now to conclude, what I would like to show is, I mean, what can be maybe a nicer application of this non-local model to a mixed human-driven and autonomous traffic flow. So for this, we can assume that we have two populations. One is the human-driven cars, and one is the autonomous vehicle population. And we describe each of these populations with a conservation law, so with the mass conservation law. So for each of the two populations, okay, here I consider any m number of population, as many as you want, but here m will be 2. We have the mass conservation, and you see that these equations are not independent from each other, but they are coupled in the speed term, because the speed of each class depends on the class itself. So there may be classes that have higher speed or lower speed, but they depend all on an average mean of the total density. That means each class of vehicle adapts its own speed to the total traffic it has around it. So R here is the sum of the densities of all the classes. And the speed here depends on this capital R. So the two equations I have are coupled by this term. Okay, and okay, these are, I mean, this is classical in multi-class models, okay? And there's a bunch of them in the literature. So the specificity here is that the speed dependence is non-local, okay? And again, I may have a different weight for different classes of vehicle and different kernel supports, so different interval of interactions for different class of vehicles. So an example of application could be the following one. I consider autonomous vehicles and human-driven vehicles. For autonomous vehicle, I suppose that they have a lot of information over the surrounding traffic, and basically their weight can be constant because they see all the cars in the same way, and they can see also very far. So the eta of the autonomous vehicle is much bigger, 2 orders of magnitude here, of the eta of the drivers, human drivers. And the human drivers behave more like we are behaving, so they don't see very far, and also they see very well what is close to them and much less what is far, so the weight is linearly decreasing here. So, and then I consider, okay, a periodic problem, so they are driving in a circle, and they start with an oscillating initial condition in which we have a percentage of autonomous vehicle and the rest of human-driven. So beta here is the penetration rate of autonomous vehicle. And this is what happened from the simulations. So you can observe the initial datum here is the green one. I hope you can see correctly the green that is oscillating. And these are the two classes of the autonomous and non-autonomous. So here I'm supposing that beta is 0.9. So I have a lot of autonomous vehicle and very few human-driven vehicle. And this is how traffic evolves according to this model. So in about time equal 2. And this is another illustration. So these are TX plots of the total traffic density. So this is the sum of the two families of cars corresponding to different beta. So beta equal to 0 means that there are no autonomous cars. And so this is the evolution of traffic described by the more or less classical LWR model, because eta is very small here. So we are basically like using the LWR model. And here is increasing, so 0.2, 0.3, and 0.9 that corresponds to the pictures I showed just before. So again, this is not intended to describe exactly what will happen on the roads when autonomous vehicle will be really deployed massively. But what I hope is that we can improve these models to describe what will be the dynamic. So these are just naive models made by a mathematician. That can give an idea of what would be, but not of what will be. Okay, so I'm waiting for suggestions, especially from engineers, to what would be good changes to do to these models in order to describe the situations correctly. Okay, to conclude, I can show you some literature. So, okay, numerical schemes are nothing very exciting for this type of model. The only problem is that since you have to compute the integral at each time step, of course, this is time and resources consuming. So you should be careful of how you compute the integral, and also you have some interest in using higher order models in order not to smooth out too much the solution. So these are some references. As I told you, this type of no-local models has also there are some extension to networks. I mean, these are first steps in the extension to network because it's not obvious how to deal with changes at the junctions. And can also be justified as micro limits. So given a micro dynamics, how you can derive these macro models. And in particular, you can also, in this paper, we also show that you can derive a second order no-local model from a micro dynamic. So I guess that I can stop here. So I have to stop here because I finished my slide anyway. I hope in time.
Thank you very much, Paola, for a very delicious and big meal that I think we will enjoy digesting.